Hi, matriculants. This is the second part of our video on reaction rates, and we stopped the last time with question 7. So let's continue and see how we can answer some more questions on reaction rates. Okay, question 7b, we still have this reaction where the hydrogen peroxide is reacting, and in this case it's breaking down or decomposing into water and oxygen gas. And this question, the first part, we must always remember the peroxide is going to react, and the manganese dioxide that we added to the Erlenmeyer flask was breaking it down, and we produced oxygen in this gas jar. Just to recap a little bit, take note that the graph that starts at 0 and it continues like that, that will be one of my reactants, sorry, one of my products. That could be the oxygen. And then the reactant will always start with a little bit higher on the graph. In this case, it will have a certain amount of moles or concentration. And this graph indicates the number of particles, so that will be moles. And you can see that it's decreasing and it will level out at some point over here. Let's see what the questions are. And there we see another graph. First part here is define the term reaction rate. So make sure that you know your definitions. I find that learners don't study definitions, and those are easy marks that you generally will throw away. Doesn't require a lot, just to remember a definition that is easy to write down. The change in concentration of the reactants or products per unit time. So remember to write in both products and reactants must be part of your definition, and don't forget per unit time. In this case, you can also say in a certain time period, but I think it's easier to remember per unit time. The second question that we have here is name two or more factors, or two more factors apart from the factors already used in this equation, which will influence the rate of the chemical reaction. Now, do take note that we've used a catalyst, so we must mention any of the other factors. You can either look at the concentration. So don't just say concentration, it must be concentration of one of the reactants. In this case, it's going to be the hydrogen peroxide. You can think of pressure, but pressure is not applicable. So check your equation to see if your reactants are in gaseous forms. That's not applicable here. Temperature can definitely be a factor because we can heat up the peroxide. So temperature is another factor. Nature of the reactants, not a factor because we're not going to change the reactants. And then surface area can be a factor. In this case, we can change the surface area of the catalyst. Instead of a solid, we can use powder, and that will increase the rate of the reaction. And for this particular reaction, we can think of catalyst. However, catalyst has already been used, as I mentioned. Manganese dioxide has been used here, so we're not going to include that one. Okay, so there we have it. The third part of this question, which is 7c, they ask us to refer to the collision theory to explain how the presence of a catalyst increases the rate of the reaction. So here you have to tell us a little bit about how the molecules are going to collide and how that collision is going to increase. And remember, the catalyst has increased the rate of reaction, so we would like to know what's happening with the molecules and the number of collisions per unit time. Now, before we're going to continue with that, let's have a look at the graph. This is the Maxwell-Boltzmann distribution graph, and the original kinetic energy was at this point, but adding a catalyst has shifted the kinetic energy to the left, which means it has led to a decrease in kinetic energy. So there are a few points that we need to mention in order to answer this question. So what I'm going to do is let's look and see what they say here. And I'm going to read the videos a little bit in the way, but I'll read through each point. The first point is a catalyst lowers the activation energy. The second part is more molecules will possess um, um, energy of will possess more kinetic energy, and that energy will give more effective collisions. With more effective collisions, we will find that the time will be shorter for the reaction to take place, or a shorter period for reaction time. You can also say, in another way, that more effective collisions will take place, or you can say more effective collisions per unit time will occur. So you don't have to use one statement. As long as you have the same idea and you give the same idea using different words, that will be accepted. Okay, the part D of this question, and this one is long, so let's read through it. You have to copy the graph of the in this case, the volume versus time graph over onto your answer booklet. And the experiment is now repeated twice with a change to one of the constant variables. The first experiment, therefore, will now serve as the control experiment. Draw the possible curves expected on the same set of axes if no catalyst is used, and that we're going to indicate as A, and then the experiment is repeated at a higher temperature, and we're going to indicate that graph as B. So if we look at our particular graph, we'll see that A is going to be lower. This part where it graph curves is going to be more towards the x-axis or the time graph. But remember, where the graph is going to end, it's going to end at the same point as the previous graph. So it's almost like the graph is a little bit more flatter. Let's see what the second graph is going to look like. B. This one is going to be faster. And because it's going to be faster, this curve of the graph is going to be more to the y-axis, which is indicated by the volume. Okay, so that indicates that the reaction is taking faster, and then a part of the graph is going to level out. So the leveling out is going to be more to the left. It's not gonna this graph B is not gonna connect there. It's going to level out a little bit sooner, and that indicates to us that the graph is faster, and this part indicates that the reaction comes to an end sooner. The original graph leveled out around about this, and that represents a certain time on the time graph of a year. But we can see that graph B, which is a faster reaction, it's going to reach the end of the reaction around about year. So that indicates that the time for graph B is shorter than that for the original graph. And those are the two answers for the first part of this question. The second part of the question, or the next question, what mass of manganese dioxide will be left at the end of the experiment? Now remember, in the previous slides, we said 1 gram of manganese dioxide was added. And because of the catalyst, and we know that the catalyst will affect the rate of the reaction by speeding it up, but it will not be consumed in the reaction and become part of the products. So that means that the same amount of products will be left. And sorry for that, we can't see it here, but the amount of catalyst that will be remained at the end will be 1 gram of manganese dioxide. Anyway, so let's continue. Question 8, before we're going to continue with question 8, we need to focus on some terminology. Please refer back to your exam guidelines, and under rates of reactions, or in the guidelines, they talk about chemical change, energy, and change. Here are some of the definitions that you need to understand and need to memorize. Heat of reaction, exothermic reaction, endothermic reaction, activation energy, and activated complex. Take note the difference between these terms and try to memorize them, because those are easy marks that you can gain in the exam. And then The second part of this will be reaction rate. What is collision theory? Uh, definition for catalyst, and then factors that affect reaction rate. Now, we've mentioned those factors in the beginning, so these are not so much definitions. These are just key information that you need to know, and you need to understand how to apply it in order to answer some of these questions. Okay, question 8b. We're going to look at what's happening in this particular part of the question. The reaction of zinc with an excess of hydrochloric acid to investigate the factors that affect the rate of a chemical reaction is given below. Now, do take note that we've done this before. When you have a metal reacting with an acid, it will always produce a salt and hydrogen gas. So that's the reaction of zinc with HCl. There were several experiments done in this particular investigation, and we need to get a sense of the information that is given to us in this graph, in this table. And we're going to look at the table. In this case, we want to see what's happening from the top to the bottom. Now, they also tell us that experiment 1 is the control experiment, and all other experiments will have slight differences, and that will be the extra information that will tell us how each of these other reactions will compare to experiment 1. Zinc, because zinc is reacting with excess hydrochloric acid, it means there's a lot of hydrochloric acid and there is enough in order for all the zinc to react, and therefore zinc is the limiting reagent. So from experiment 1 to experiment 4, the mass remains the same, and we can see that experiment 5, the mass has doubled there. So that's the difference. So we're just getting a sense of what's happening. In the second column, state of division, the zinc stays all the same, they're pebbles, except for in experiment 4, there's powder. In concentration of the HCl, all the reactions are 0.5 mole per cubic decimeter, except for reaction 2, where they've changed the concentration and it became a little bit more or higher, and that is 0.8 moles per cubic decimeter. And then in the last column, we have the temperature of the HCl, and we can see that almost all of those particular experiments have 25 degrees Celsius, except for experiment 3 that has 35 degrees Celsius, and that one is a little bit hotter compared to the others. So there we've got an overview of the table, and we may continue to answer the rest of the questions. So we can see, before we're going to continue, that there are several ways that you can calculate the rate of reaction. We can use concentration divided by time, we can use the volume by time, and we can also use the moles divided by time. And if we're looking at our equation, we just want to refer back to it. So we place it there again. And the question reads as follows. Calculate the average reaction rate, in this case in moles per second of reaction 1, if the reaction takes 2 minutes to complete. So based on the unit, they are giving us an idea of which formula we're going to use. We're going to use this one. We want to know the moles and the moles per time unit. And our calculation is going to be as follows. Now remember, they've given us 1 gram of zinc, so we can't just take the 1 gram and substitute in the final equation. We first have to convert that to moles. And in this case, we see we get 0.015 moles of zinc, and we'll take that and substitute it into the rate equation, and that will be delta N divided by delta T, and that gives me, because the amount of zinc at the end will be 0, but the amount of zinc in the beginning will be 0.015. So that will be the final value minus the initial value divided by 120 seconds. And that gives me an answer of 1.28 times 10 to the power, if I've got it correct, and I remember it's -3 moles per second. And that tells us that is the reaction, the average rate. Now, in this particular case, what we've measured is the rate of the zinc. If you're going to take note, your answer should be negative. And I missed that negative. I didn't put it in there, but it's quite okay if you leave it out. But in most cases, I would say put it in. It's negative 1,28 times 10 to the power negative 3 moles per second. Okay, that's the answer for that question. Let's look at the next one. And here, just take note that in most cases, rate reactions are curves. So when we're going to work out the average rate, what we're actually calculating is the tangent to that curve at a particular time, and that will be over a time period of 120 seconds. Okay, so that's just a graph to indicate to you how we've calculated that rate of the reaction. Okay, we've come to the end of this particular topic, and we want to summarize so that we can get a sense of what we spoke about. The first part, we looked at the collision theory, and we said that particles must have sufficient energy when they collide, and the second condition for the collision theory was they must have the correct orientation. Remember those two conditions, both of them must be met. Then we looked at what constitute an effective collision, and we indicated those effective collisions on graphs. And it's important that you need to know that those effective collisions can be affected by 6 factors. Now remember, I said in the beginning that there are actually 5 factors if you have a homogeneous reaction. So that means if both your reactants are on the same phase. And then a 6th factor comes into place. That is the nature of the chemical reactants. That one comes into place if you have a heterogeneous chemical reaction. So we've decided just to put in 6 factors. So take note, 5 you will see in most cases of your books, but they also explain that there's a 6th factor that comes into place. And those factors I've highlighted here by just giving you the first letter of each factor. And you know by now this is concentration, that's pressure, temperature, nature of the reactant, surface area, and that last one is for catalyst. And then the third part is when we're going to do calculations for the rate of the reaction, the average rate, it's important that you take note what particular rate you have to calculate. Is the rate of the reactant? Is the rate of the product? If it's a reactant, remember the reactant is used up. So my answer will generally be negative. And you'll start your equation by saying negative delta C. If it's the concentration over delta T. If it's a product, our equation generally is a positive. Now take note, these are the 3 formulas that we're going to use. So you can use any of those to calculate your rate of your reaction. And then lastly, we have to understand the graphs. We've done these graphs in grade 11s with energy potential graphs versus reaction time. And we've looked at this, in this case, is an exothermic reaction and what happens to the product's energy. How does it compare with the reactant energy? And this graph that we've learned about this year is the Maxwell-Boltzmann distribution curve. Make sure you know all 3 graphs and how the graph changes with a change in a factor that's going to influence the chemical reaction. And yes, grade 12s, that's it. We have looked at all the parts and we've looked at some of the questions. I know there are more questions and I hope that you will use these questions as a foundation to answer some more questions. I wish you luck with this particular topic and all of the best. And for now, we have to say goodbye. Thank you.